So today we will continue talking about applications of cohomology. Just to review what our goal is dimensionality reduction, which basically means we just want some kind of map. It would be great if it would be an embedding. It probably won't, but we'd like to somehow, in some manner, preserve the structure of the data. Most reduction methods just go into Rn, one component at a time, maybe projecting along principal components or other methods. What we want to look at is projecting onto S1 because we know that data has holes, and so having some of our component functions projecting onto circles might give us a better representation of the data. We will use the fact that a circle is a ring, so we can multiply two angles. Or we can add two angles together, and we would still have points along the circle. Any questions so far? Okay. So we have here some data points. So we see all these data points right here. We want to create a map to a circle. And one potential map is to basically send all the yellow points over here to the yellow over here, the red over here to the red over here, etc. And so we can create this map from our data that clearly looks pretty circular onto a circle over here, basically preserving the circle structure. So that's our goal, and the way to achieve that goal is to look at persistent cohomology. So to take a look at cocycles that are persistent and use that to come up here and create this map. We have a lot of cocycles, that are not, that they're born, but then they die very soon. So remember, the x-coordinate is the birth time, the y-coordinate is its death time, and so this was born here, died very shortly thereafter. If you take one of those and use that to create your map, well, then you get a map like this. So I am not sure exactly which data point, but suppose we took a look at this data point and created our map from that. Well, you can see that almost all these points just get mapped to here. And so that doesn't really preserve the structure of the data very well. Much of the data just gets smashed. Yeah, we might be able to see this circle here, but that's not the circle that we're interested in. That circle does not persist. And so you want to find the circles that persist via cohomology in order to come up with this map instead of this map or other maps. So that is the motivation. We now want to go ahead and just quickly review what cohomology is. So remember, we have our same finite simplicial complex. That's the same thing whether we talk about homology or cohomology. We've got vertices, edges, and faces. The only difference is we're going to use superscripts instead of subscripts, but our finite simplicial complex is the same thing. Where the difference comes in is we're interested in cochains. So in terms of cochains, we want to look at functions on our vertices, edges, and faces, etc. And so we're going to look at the collection of functions on here because, after all, we want a function from our vertices into, if we choose our ring to be S1, then we get a function from our data into S1. Now, in reality, the rings we're going to look at in order to create this function will actually be into the real numbers and into the integers, but we will then collapse the real numbers mod the integers in order to create S1. So we will be looking at the sets of cochains where our functions go into a variety of rings, including the real numbers and the integers. So, but this is our set of cochains. This actually, we did mention that in reality, we were actually going to talk about the simplicial complex, not just, take the entire simplicial. So here, so we talked about mapping from the linear combination of, say, faces or the linear combination of edges. So we can extend that map to the linear combination of faces or linear combination of edges or linear combination of vertices. But since we are required to extend linearly, the map is defined just upon where the faces go. We don't need to look at the linear combinations in order to define the face. In order to define the function. So if our function is defined on edges, we can extend it linearly to go ahead and define it on arbitrary linear combinations of edges, so our one-dimensional chains. But since it extends linearly, we will just focus on our functions being defined on the simplices and not the entire linear combinations. Questions on that? I just noticed that there was a chat. Is everyone getting the video and audio okay? Okay, good. Yeah. Okay. So then we have our coboundary maps. Our coboundary maps go in the other direction in terms of, so we're going to go instead of, so the difference with cohomology is we reverse the direction of the arrows. We go up in dimension. So if I have a function defined on vertices, I can create a function defined on edges, and the way we create it is we're assuming everything is oriented. So I define this function on this edge to be f of b minus f of a. So we remove the first term, becomes f of b, remove the second term, minus f of a. So we do this alternating sum. If I take a map on edges, we can then create a map on faces where the map acts on a face by just delete a and do alpha of bc. Alternate the sign, delete b minus alpha of ac, delete c, and do plus alpha of ab. And so we can go up in dimension where if our function acts on vertices, we then can go, if our function acts on edges, we can then create a new function that acts on faces. We will often use alpha just to help us distinguish when where our function is acting on edges versus when it is acting on vertices. But of course, we can use any letter we want, but just so that we can determine from our context, alpha will frequently be used when our function is acting on edges. Any questions there? We then have very similar definitions to what we had. So there's a lot of relationship between homology and cohomology. We just do cocycle if it's in the kernel. So that's what we did last time. We had cycles if it was in the kernel. Now it's cocycles if it is in the kernel. What does it mean to be in the kernel? Well, that means that this thing here is the zero function. So it's the zero function. So whenever it acts on, it's the zero function. So if I take di alpha and have this function act on some simplex sigma being the zero function, I will just get 0 out. So we have the zero constant function. So it's a cocycle if it's in the kernel. It's a coboundary if it's in the image. So same definitions that we had from homology. So we just would need a function in our lower dimensional space to be sent to our alpha, and that makes alpha in the image, and so then we would call it a coboundary. We have, just like we had with homology, if we do two of these operations, we do get the zero function out. That implies that our image is contained in our kernel, and so we can again do kernel mod image, but now we're doing our cohomology, so we do our superscript here to indicate we're doing the cocycles mod the coboundaries. But very similar definitions to homology. Let's take a look at an example, and we can see that we can compute this in a very similar way to our homology. We can do basically very similar things. The only difference is we now have functions. So our set of zero chains, since our functions are, in this case, our function is on vertices, we only have 3 vertices. So our function acts on these 3 vertices. So as soon as I specify where these 3 vertices go, then I know what my function does. So we just have to specify where the 3 vertices are sent in our ring. Same thing with C1, it's functions on edges. Well, in this example, I also have exactly 3 edges. So once I know where these 3 edges go, then I know what my function is. And we want to calculate our cohomology for this simple example right here. In our simple example, we can see that we've got vertices, we've got edges, we don't have any faces, so the only function we have is the zero function, so we just have 0 out here, and we don't have anything in the -1 dimension, and so we have 0 here, and so this is our sequence of cochains that we have right here. Questions up to here? We can now do our kernel mod the image. We'll do our case for H0 first. So for H0, we're taking a look at this thing right here. We want to know the kernel of this map, what gets sent to 0 here. And then we know that the image will also get sent to 0, so we want to mod out by this image. Well, in this case, our image is pretty easy. What's the image of 0? It's just 0, so we're not modding out by anything. So we're not modding out by anything, so we're just going to have the kernel of D naught right here. So this thing right here will just get the kernel of D naught. Any questions up to here? So we've got our kernel of D naught, so we now want to calculate the kernel of D naught, which means I want to know what gets sent to 0. So I basically just want to take, so I'm now concentrating on this in order to find the kernel. So I'll take an F in my C naught, and I want to know when is D naught of F equal to 0. Well, to determine that, I can just take a look at what my F's do. Well, my F's are right up here, and I want them to give me something that is 0. So let's take a look at that on our next slide. If my D naught F equals to 0, well, we know what D naught F is. D naught F acts on the edges, so it's now going to be a function on edges. So we had a function on vertices. D naught F gives us a function on edges. To see where it goes, we only have to check to see the 3 edges it can act on. If I checked how it acts on the edge V1, V2, it's going to go do F of V2 minus F of V1. If I want this thing to be the 0 function, then this must equal to 0. And so I would need, in order for F, if F is an element of my kernel of D naught, then I would need F of V1 to equal F of V2 so that I get the 0 function out when I do D naught of F applied to any edge. So we can do that to any of the edges. D naught of F also acts on the edge V2, V3, but by definition, it is F of V3 minus F of V2. We said that D naught F is in the kernel, so it equals to 0. So we get F of V2 equals to F of V3. And similarly for the last edge right here. And so in other words, we get F of V1 equals to F of V2 equals to F of V3. So when is F in the kernel? So when do we have F is in the kernel? Well, when F is in the constant map, and it must be the constant map. If I do have the constant map, then when I subtract these things out, I will always get 0, so it will go to the 0 function, so it will be in the kernel. And if it is in the kernel, well, then I need it to be 0, so then I get that it is the constant map. So F will be in the kernel if and only if F is the constant map. So we know what the kernel is as long as we've got it equal to some constant, so all our vertices get sent to the same point in our ring. Note what this tells us, so think about what this tells us in terms of components. If two things are in the same component, then their function values are going to have to be the same, because there will be some edges leading between them. So if there's one edge or a sequence of edges connecting them, V1 to V3, then we will eventually get that F of V1 equals to F of V3, and so we will get the constant map on each of the components. So for a function to be in the kernel, we're basically determining the number of components. So we'll have the constant function for each component. Questions there? So if we now want to calculate our zeroth cohomology, in our zeroth cohomology, we do our kernel mod image, which was just our kernel, and we just get that our kernel is just the constant map. And this, by the way, will be equivalent to our ring. You know, for each R, there is a function that sends vertices to an element of the ring. So I can send this to my ring by just sending my function if f of vi equals to r for all I will just send that function to r. And I can add these functions here just fine. Adding these functions means that I would send f of, if I do f plus g would be sent to r1 plus r2, where f was the constant function going to r1 and g was the constant function going to r2. And so we can have this being exactly the same thing as the ring, so we can think about this thing as being equivalent to our ring right here. So any questions about that? So note the similarities between homology and cohomology. Our computations can actually be done in a very similar manner. Let's now take a look at our first homology, our first cohomology. In our first cohomology, we're now taking a look at this. I want the kernel of this, mod the image, all of these things go to 0, so mod the image of that. Well, in this case, what's my kernel? What gets sent to 0? Well, everything gets sent to 0 because that's the only option. Since we've got a 0 on this side, that's the only option, so our kernel is trivial to calculate in this case. It is just the set of 1 cochains. So the only thing we need to care about is the image of our D naught. So we just need to worry about calculating this. Any questions about that? So now we want to focus on calculating what is in the image. So I want to take a look at what's in the image of D naught. So I'm looking at this map right here, my D naught. Well, what's in the image is if I take an F, it's going to go to D naught of F. So I basically, this is exactly what's in the image. This is exactly, what we're going to be getting in the image. So all I need to do is understand these maps D naught of F. To understand those, I can just take a look at the definition of D naught of F. So I know that this D naught of F is in my image. And what does D naught of F do? Well, it's in C1, so it acts on our edges. And we have the definition. So we have this nice definition right here. Well, I want to do C1 mod the image, and I know what the image is. It's just the collection of these maps right here. Well, I would like, however, to relate the image to C1. So let's see if I can relate the image to C1. Well, in C1, if I take a look at C1, this is my C1 right here. It's the map that will send an edge E1 to R1. Well, E1 is my edge V1, V2. So this is my edge E1, and this is my edge E2, etc. And so if I take a look at an arbitrary one cochain that may or may not be in the image, then I know that alpha of E1 will just be, it's defined by choosing the element in the ring it gets sent to. Well, D naught F, is there a D naught F that will send my edge E1 to an arbitrary point in my ring, such as R1? Well, yeah, I can go ahead and get this thing to be R1 by just choosing a function. I've got lots of functions. These functions, my F goes from my vertices to my ring. Well, I'll just choose a function that sends my vertex 2 and my vertex 1 to something where their difference is R1. I've got lots of functions to choose from. I get to send F of V2 to anything I want to. I can send F of V1 to anything I want to. I'll choose something such that their difference is R1. Maybe I'll send F of V2 to R1 and F of V1 to the additive identity 0. So that's something, R1 minus 0 would give me R1. Doesn't matter what I send it to as long as the difference is R1. So does everyone believe that I can do that? So any questions about that? So similarly, I can send F of V3 minus F of V2 to something where the difference is R2. So I want alpha of E2 to be R2 to get this arbitrary function alpha out. So if I sent V2 to R1 and V1 to 0, well, then I can still send V2 to R1, but then V3 to R1 plus R2. So that's an example of something that we could have chosen. There's lots of different choices. I just need to make one choice that then sends me to this thing right here. Any questions so far? Well, I've already chosen where V1 gets sent to, and I've already chosen where V3 gets sent to by F. So now I have that this thing is uniquely defined. And so if I had sent this thing to 0, R1, R1 plus R2, well, then I'd have 0 minus R1 plus R2, and so this thing would be minus R1 minus R2. Whatever we happen to, it doesn't matter what we send it to, as long as the difference is R1 here, and the difference is R2 here. And if I take this and subtract off this, my F of V2s will cancel out, and I get my, if I need minus, so if I do minus of this plus that, then I'll get minus R2, sorry, minus this minus that will give me minus R2 minus R1 on this side, and on this side I will get minus F of V1 minus F of V3. And so we understand our function D naught of F. I can create D naught of F to be any function where the first two things. The first two edges, E1 and E2, can be sent to anything, but then the third edge will be determined by where our other two edges go. Any questions on that? We may be using the language of functions, but what we're doing is very similar to what we did for homology. So we took a look at this thing here, and we just said, if I take a look at the image, oops, the image, I have a typo in this thing. Does anyone find the typo? Well, if I want to have a function on edges, it should be d naught of f. And so this one here should have been d naught of f. It would be the collection of all functions that are in the image, so d naught of f, where are d naught of f, these should all be d naught of f, where d naught of f is these things right here, and we saw that we could go ahead and choose that. And so any questions about that? Sorry for that typo. I will correct that before posting the slides. So if we are now doing this, we are basically saw that we could get out the function. Actually, I could have used any letter here. The image is, it doesn't matter whether I called it f or alpha or d naught f. I prefer d naught f because we were using f for a function on vertices. But I could have used f as a function on edges, or alpha on functions of edges. So actually it wasn't that bad of a typo. Mathematically, it was perfectly fine in that I do have, my image is just the collection of functions that acts on edges, such that my function on edge E1 and on edge E2 is completely arbitrary, but the function on edge E3 must be minus R1 minus R2. And if my function does that, then I know that there exists an f such that d naught of f equals to alpha. I'll actually change all of these f's to alpha, but we know we're requiring that this alpha to have this f such that d naught of f equals to alpha by making this requirement right here. So as long as I've got that requirement, then I know such an f exists and it is in the image. Any questions on that? So what we now have is my set of one cochains. So here I'm using all f's. I could use all f's or all alphas. Is that I have functions. These functions are acting on my edges. So that's my one cochain, is the collection of functions acting on my edges. I mod out by the image, which is my collection of functions acting on the edges, such that if I know where E1 and E2 goes to, then E3 must go to here. So in other words, we're only, we mod out by, doesn't matter where E1 and E2 goes to, we only have the restriction on E3. And so this is, again, isomorphic to our ring. So it's isomorphic to our ring again, because we just have this one difference here. We can, similar to our homology, sort of say, oh, these restrictions are the same. This is arbitrary. This is fixed. And so thus we get just one component that is different between our C1 and our image. And so we just have one component of our ring and be isomorphic to that. And so we can send our functions to basically wherever. So in this case, if I would send my function in my one cochains into the element in R3 corresponding to R3, and that would define my function right there. So we can calculate our cohomology. Any questions about calculating cohomology? If we can calculate cohomology, then we can calculate persistent cohomology. So in our persistent cohomology, we do exactly the same thing we did before to get our simplicial complexes. So we will have our epsilons in increasing order. So maybe I'll start off with epsilon equal to 0 and just have my vertices. And then maybe my epsilon will be 1, and then maybe it'll be 2, etc., and just increase our balls. And we will create our simplicial complex. So this will be the simplicial complex, where in our first case, epsilon 1 is 0. And so I just have my 3 vertices. So we'll have this being epsilon when our radius is 0. And then we increase our radius. We start seeing some things intersecting. So in here, when we've got this radius right here, this doesn't intersect with anything, but these two do intersect. And so we've got an edge between them, and so we have this edge. So if that corresponds to a radius, say, of 1, we'll have this being the simplicial complex corresponding to x of 1. And then increasing the radius, eventually they all 3 intersect. And so if they all 3 intersect, we will still, I drew the Rips complex, which in this case was also the Chex complex. So whichever complex you want to work with, you can do the alpha complex, whichever complex you want to work with. We just need to create a simplicial complex. So create the standard simplicial complex by going ahead, and if they intersect, we'll add this, and then we'll either add in all higher dimensional simplices with the Rips, or just the ones that intersect for the Chex, etc. So here we have exactly the same thing as we had before, just our standard simplicial complex. What is new now is that we're now going to go ahead and take a look at our cochains, which will be functions on this. So now we're going to have a function from, when from our x0 into our ring, or our function from our simplicial complex at time 1 into our ring, or our function at time 2 into our ring, etc. So now we'll take a look at our cochains, but notice that our arrows are going backwards. Why would we put our arrows backwards? Well, I need to be able to take a function here, so maybe I'll take a function here that goes from this over here, and our function might be acting on, say, just our vertices maybe at time 1, or just our edges, or just our faces, whatever we have. So our function will be going from that into our ring, and I want to send that to a function over here. Well, the way to send that to a function over there is first for me to clear the page so I've got more room to write. So I've got a function that acts on vertices, edges, and faces, etc. at time 1 and outputs elements in my ring. And I want to send it to a function that acts at time 0 into my ring. Well, there's a very simple thing to do. I can just take this function here, let me call it f1. I can take f1 and restrict it to x0. So we can just do the restriction over here. So this would be the restriction of our function just acting on x0. And so since we know that this, as our simplicial complex increases, if I've got a function acting on this, well, then that function is going to act on a subset. And so I can just restrict the function. And that is why our arrows go the other way, is we're just taking a look at taking a function here, and then we will just take a look at that function and restrict it to our simplicial complex with potentially fewer elements in it. Any questions on that? And so once I have that, I can then create my homologies. So once I have this, that will induce a map on my homologies where I can take a function here. If it's a cocycle, I can check to see if it is still a cocycle once we restrict this thing over here. And so we can induce maps on our cocycles and our coboundaries. And so we do have one on homology as well. Any questions there? So this is our persistent cohomology. One thing to note is cohomology is very similar to homology. We can, again, do our epsilon thing. So if we have a cycle that gets created at this time here, let me again clear my screen. If I've got a cycle that exists at this time here, I can wonder how long it lasts. So we can take a look at, say, we can take a look at these things and see how long they last. So we can do similar things in terms of our cohomology. However, when we do this, for those of you who know about cohomology, there are big relationships between homology and cohomology. We've got Poincaré duality that tells us how cohomology is related, as well as Alexander, the things, the universal coefficient theorem. There's a lot of things that relate cohomology to homology. And we actually will get exactly the same persistence information out of this. So this right here actually won't give us additional persistence stuff. But what it will do is it will give us the maps. We want the map. I want the map here into my ring. I want this map. And so that's why we wanted to go ahead and take a look at persistent cohomology, is so that we get this map of how our things begin and end. We want to know a persistent cocycle that will then give us a map, say, on this thing here, see how persistent it is into our ring, and then come up with maps on our simplicial complex. So that's why we're interested in cohomology, is because we actually do want the map right here. There is other reasons people are interested in cohomology. One can add a ring structure to cohomology, which will get you a lot more information to the homology groups. So it is true that as groups, if your homology groups are isomorphic, your cohomology groups will be isomorphic. But we have this additional ring structure. If anyone is interested in us discussing that, find a nice application regarding data analysis, and we will discuss that. But unless there is a particular application you're interested in doing, this might be the only cohomology stuff we're doing. It might be just this one example. But if there is an application that you're interested in, do let me know. We can take a look at that ring structure. I did hear a talk yesterday about using cohomology to basically program a robot to do what you want it to do. So there are some interesting applications out there. So any questions? So let's take a look again at our getting our functions. So remember, we took a look last time that if we've got a cocycle, so if I do have a cocycle, then I do have a continuous function that I can extend to my entire space out of here. So this is a cocycle. It would actually be modded out. If I mod out by the coboundaries, it will go away. But we do have a cocycle here. And according to this, I can come up with a continuous function on my entire simplicial complex into the circle, such that every vertex gets mapped to 0, and each edge gets mapped to the winding number alpha of AB. And so let's see what we mean by that. Well, the proof of this is actually pretty simple. The proof is to say, I want to map every vertex to 0. Well, that's simple. I will come up with a map where I will just define my map. I will just define my theta of VI. and just send it to 0. So my theta of VI, all of these just get sent over here to 0. So that's the first thing. Then I will define my map and say, what does it do on my edges? So where does theta of E1 go to? So I want to define where theta of E1 goes to. Well, I take a look at alpha over here, and I take a look at where alpha of E1 goes to. Alpha of E1 is going to some integer n, because in this case, my ring, we chose to be the integers. And so alpha of E1 sends this ring to some integer. I want to send this thing to winding number alpha of AB, so I'm going to want the winding number to be n. In other words, I'm just going to send this edge to make it wrap around this thing n times. And I can do that. I'll just say I will send, this point here, I'll partition it into n things, and each of these n things will wrap around once in the same direction, and so that tells me where my edge E1 goes to. And if my edge E2 goes to, say, -3, well, then I will go -3 times around so I'll partition this thing and send this thing to -3 times around. And then wherever this thing goes, if it goes to 1, we'll go ahead and send it 1 around. And so now I've defined my theta on all my edges. Any questions so far? I then have to come up with a map that sends the space someplace, and I want it to be continuous. What that means is these 2 points over here are close, so I want their images to be close as well. So the images should also be close. Well, let me illustrate that with a simpler example. So let's go ahead and just say I'm going to go ahead and, it's not the same one, but we'll map both of these vertices onto here. I am going to map this edge onto here, and then I will map this other edge onto going the other direction. So I'll map it that way. They're going onto the circle. I just try to keep them offset, so they're both going onto the circle. Just want to say, so we can sort of see what's happening here. So I've gone ahead and sent this outer circle to S1, and that's how we had already defined. We had defined this on edges and vertices, so our outer circle, we know where to go. Now I want to figure out where to send the other thing. So maybe I want to know where to send these points. Well, I want these points to go to points that are close to the red points. Well, the red points went in this direction, so I'm going to send my green points in this direction here as well. But I'm actually not going to go all the way, so I'll go a little bit slower. So instead of hitting this vertex here, I'll go basically whatever this distance is away. I'll keep that, keep this sort of distance away here. And then, well, it'll be related to that distance. And then when I go this direction, well, the blue one went back. I'll send the green one back here as well. So it all goes into the circle. Let me clean up that picture again. It all goes into the circle. My first one, the outer circle, will do this kind of thing. The next one will do something similar. It just won't go quite as far. The third one, so the further in I go, the further in I go, I just don't go all the way around the circle. And that makes sense because my first circle, this circle right here, in the first half it did this and then it went back. I've got a nice continuous function because I'm just doing something very similar, just doing it a little bit less each time, and so I do get the continuity that I wanted. Any questions on that? The only problem with this is that I sent all my vertices to 0. All my data got sent to 0. That's not a very interesting function. This is what's called a useless mathematics theorem for my data. But in math, we frequently come up with the useless ones first so that we can then get the one that is useful. So this one here is much more useful. In this case, that was just repeated in case I needed the figure again. So actually it was to remind me to say we can do similar sorts of things, that even if our outside circle now is doing, if this outside circle is doing so many times around here, but then goes backwards in the same thing, maybe more, but then the last edge makes up for it, you can do the same sorts of things. You'll just in each case go not quite so far in terms of when you're coming up with these inner circles here. So you can still extend in the same way that we extended this thing here. So we can now go ahead and come up with our useful theorem. In our useful theorem, we now have more hypotheses. We've got a cocycle where our ring is now the real numbers. And we also have a cochain, a one cochain, using the integers as our codomain, as well as a 0 cochain here, such that our function alpha bar is going to be the sum of these. So this thing does act on edges, gets out a real number. This one acts on edges, gives out an integer. An integer plus a real number is a real number. So we can go ahead and add these two, even though their domains are different. But I can do an integer plus a real number, so I can get into the real numbers. So if I've got that, then I do have a continuous function again that goes into here, where now we just have each map here goes into edge maps linearly into something of this thing right here. So let's say what we said about linearly. In reality, the theorem actually states we're going into R mod Z. So we're actually going into the real number line. But into the real number line, my edge is going to be mapped, say, from 0 to n. So if alpha bar, actually, let me just put pi, for example. Maybe alpha bar of my edge equals the real number pi. So it might equal to the real number pi. Well, we can use this projecting onto the circle, saying that we'll mod out by the integers. And so if it goes around 3 times, but a little bit more, we'll go around here 3 times, but a little bit more. We then map to this point right here. And so our theta of E1 will just actually go to 0.1415 ... We just remove the integer part. And so that's what this is. It appears we will need to finish off this paper next time, and so we will take a final look at this paper and a brief introduction to bottleneck distances on Friday. Any questions for today? So then see you Friday.